and I am very glad to attend this meeting. The title of my speech is Cross-Domain Gesture based on spatial temporal feature sequences using mmWave radar. The full paper was completed. YiHui and GuoQing. We are all from the School of Computer and Information, Anhui University. With the advent of an internet era, artificial intelligence and other technologies are developing rapidly, and the way of human-computer interaction is also evolving. Traditional keyboards, mice, and touch screens are widely used, but are they natural enough and in line with human habits? Thinking about the possibility of using gestures to control or interact with devices. Gesture control technology has emerged, allowing us to interact with devices through natural movements, as if we were communicating with people.
Recognition technology based on vision sensor has potential, but it also faces some problems. One of the main challenges is the sensitivity to changes in light intensity. This may lead to impaired accuracy of gesture recognition. Cameras as sensors may have potential security risks. It may capture users' private information or personal space.
Although the gesture recognition method based on wearable devices has potential, it also faces some challenges. First of all, wearable devices have some difficulties carrying and are not convenient to carry around, which limits capability. Second, their applicability is limited to specific scenarios and not applicable to all situations. Finally, operational complexity is an important issue that may impose the burden on users, which also imposes some limitations. Gesture recognition technology based on radio signals, such as Wi-Fi, has some challenges. First, it usually has a resolution, which may limit its ability to recognize details and find gestures. Secondly, the influence on interference is large, which may lead to misrecognition or interfere with the accuracy of gestures. This technology may not be able to recognize complex, detailed gestures, which may be a limiting factor in some applications. mmWave radar technology has unique advantages. First, it has high granularity and precise angular resolution, which means it can capture small movement gestures. It performs well in applications such as gesture recognition and human body tracking. The accurate perception helps to improve the accuracy of user experience and interaction. Second, mmWave environment, mmWave radar can still operate stably. The possibility of false recognition and data interference is reduced, and the reliability and stability of the system are improved. Finally, mmWave radar chips themselves have low power consumption and compact size, making them ideal for embedding in portable devices. Traditional signal processing involves multiple dimensions of data, where the first dimension is the number of truth samples. The second dimension represents the number of truth samples per frame, while the third dimension corresponds to the number of antennas. Through a series of processing steps, including range FF2, Doppler FF2, and angle FF2, to convert the 3D regional signal into a huge 3D database. In this database, each data point contains information about the target and represent the background nodes, while only a few are the real target points. To better understand and utilize this data, constant false alarm rate filtering method is usually applied, so as to extract a discrete three-dimensional point cloud from a huge three-dimensional data block. Each point in this sparse point cloud corresponds to the position and angle information of the target, but because the data points are relatively sparse, therefore, there are challenges in abstraction and object recognition. This sparsity may lead to a decrease in the accuracy of object recognition because of the limited information of valid data. We have adopted an innovative data processing method which no longer uses the traditional form of three-point cloud. Instead, a more dense block of data is selected. The core steps of this new method are as follows. First, we'll perform FF2 fast Fourier transform on the data according to the two dimensions of the number of truth samples and the number of antennas. This results in a two-dimensional dataset, with one dimension representing distance and the other representing velocity. Through this transformation, we can measure the distance between the target and the radar and present the data in a more structured way. Next, the range FF2 transform, which processes the range information to improve the signal-to-noise ratio. Range techniques are used to accurately determine the range of the target and to distinguish the target from background noise. The distance data we obtained are clearer and more reliable. We then perform a Fourier FF2 transform to obtain the velocity characteristics of the target. This step allows us to accurately measure the speed of the target, but it is often affected by static noise during the speed measurement. In order to solve this problem, we introduce moving target indication processing technology. The accuracy of velocity measurement is further improved and filtering out the static background and noise. This new data processing method not only improves the quality of data, it also greatly enhances the ability of the system to capture the target distance and information. In gesture recognition, we'll generate a series of RFDMS Doppler on-power profiles. Each RFDM represents the distribution of Doppler information at a specific spatial point, which helps us to understand the characteristics and dynamics of gestures. To better recognize gestures, we need to extract information about spatial and temporal features from these RFDMS. First, we'll use a convolutional neural network to process computer images. Other and of the performance of gestures at different spatial points. Second, we introduce a temporal convolution of CCN to process RFDM sequences. CCN is an excellent technique for modeling temporal space data. In our case, CCN is used to learn the time dependence in the whole RFDM sequence. It means that it can capture the dynamic changes of gestures, such as the movement of gestures, speed changes, and so on. Finally, we'll combine CNN and TCN to form CNN-TCN augmented model. This model, considering both spatial and temporal characteristics. By considering these two aspects of information, we can achieve this model is specifically designed to process channel time series data and perform multi-class classification tasks. Its core architecture includes dimensional convolutional neural network and temporal convolutional network. Its workflow is a multi-channel time series data input. First, the model receives the observations relationship comprehensively and they the maximum to extract a two-dimensional feature representation of the input data. This process is repeated many times, gradually reducing the size of the feature map and extracting higher level features at each step. This helps the model to understand dimensional convolutional neural networks. One-dimensional convolutional layers are used to capture long ranges in time series data. Those convolutional layers are connected to each other by an add layer to enhance the feature representation capability. This structure allows the model to better understand temporal relationships in the time series, such as trends and periodicities. TCN model, temporal convolutional network, TCN, is used to series data. TCN is a structure that can effectively capture long-distance dependencies in time series. The input data to be convoluted across the time dimension to better capture the dynamic patterns in the sequence. Connected layer is applied after each time step of the TCN output to produce the final output. Multi-class classification task. Finally, the model applies its output sequence to a multi-class classification task. This means that its goal is to classify time series model learns to effectively classify categories of data. Value for gesture test set. The rest of the samples are used as the training set, and then the model is trained and tested. This process repeatedly, record and collate the prediction results of each test set, and finally, recognition rate is an astonishing 98.4%. This result shows that our neural network model gesture recognition. This achievement is mainly due to the fact that there are similar characteristics between the data and the test data. This means that our model can effectively capture the two features of gesture motion. Validation method will demonstrate the superior performance of the proposed neural network model on gesture recognition, which is useful for a variety of applications, such as gesture-controlled user interfaces or motion capture value. Experiments are carried out by selecting data from different locations in the gesture dataset to verify our proposed neural network model under different locations. The gesture can be established. The data at the position of 0.750 degree was used as the training set, and positions were used as the test set. The experimental results show that the recognition accuracy is mainly affected by the position relationship between the hand and the radar. When the radar distance is too close, the multipath effect is serious, resulting in a slight decline in accuracy. As the distance increases, the signal-to-noise ratio and the accuracy decreases slightly. In addition, the angle between the hand gesture and the radar affects the range of the mean loop, the received signal energy, and the Doppler frequency. Nevertheless, our system achieves in different locations, averaging 97.2%. This shows that our model is robust and to the influence of position change on gesture recognition. Different environments have different room sizes, office equipment placement, and layout, which leads to different multipath effects. In order to verify the neural network model in different environments, gesture data sets are collected from 3 different environments, in which the classroom data set is used as the training set. The 2 data sets of the conference room and the used as the test set. The experimental results show that different multipath effects do have an impact on cognition effect of neural networks. Nevertheless, the recognition rate in the conference room is 90. The recognition rate in the conference hall is 98.5%, and the recognition accuracy high. It shows that the model has strong robustness. To further verify the effectiveness of the network, 3D learning networks for behavior recognition for comparison, 3D CNN, CNN plus LSTM, and CNN plus GRU. These networks are all based on convolutional neural networks. They are different in dealing with spatial temporal features. The experiment is carried out on the gesture dataset. Results are shown in the table. It can be seen from the table that the recognition rate of the action in network is better than that of other networks. It shows that it can better extract spatial features and adapt to different action categories. Among them, CNN can only extract spatial features, not capture temporal information, so its performance is the worst. CNN plus LSTM and CNN plus G temporal features, but the calculation of the loop layer is large, and the ability to model long-term dependencies is limited. 3D CNN uses a 3D convolution layer, which can extract spatial temporal features at the same time, but number of is also large. Moreover, the treatment of time dimension is not flexible enough. In contrast, the spatio-temporal convolution layer and the fusion layer, it can adaptively extract the spatial characteristics of different scales and stages, and dynamically integrate the information of multiple branches, all as to achieve better effect. Thank you. That's all for my speech.